Hello everyone, myself Dr. NCH Ramgopal, working as Associate Professor of Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to the course Computer Oriented Statistical Methods, and in today's session I am going to discuss about stochastic processes, part 1, and the overview of today's presentation. Today I would like to introduce the topic stochastic processes and what is the definition of stochastic process and what are the examples and mainly the applications where we use this stochastic process and where we apply this particular topic, and then specification of stochastic process. Coming to the introduction, in the theory of probability, the static aspect of statistical theory has been dealt. So, the static aspect of statistical theory, whereas to deal with the dynamic aspect of statistics, dynamic aspect means the statistic of change, the phenomena that take place with change in time. So, the phenomena that take place with change in time, which is called the processes. So, to deal with the dynamic aspect of statistics, we use this stochastic process. So, in particular, the phenomena that take place with change in time is called process. A theory has been developed to study random variables depend on one or more discretely or continuously varying parameters. So, here the random variable, for example x, it has the values x1, x2, x3 and so on. So, this random variable depends on one or more, sometimes it can be discrete or continuous. So, it depends on one or more discretely or continuously varying parameters, and those parameters are the random variables, and this process is called the random process. So, it leads to a new concept of indeterminism in dynamical studies, which is called dynamic indeterminism. So, in stochastic process, we deal with the phenomena that take place with change in time. Now, stochastic process, a system that changes over time in an uncertain manner. So, that is called stochastic process. So, a system that changes over time. So, that means it depends on time. With respect to time, the change occurs in the system, and that change is also uncertain. That's why this is we relate this topic to theory of probability also. And there are some examples given here for stochastic processes. The first one, automated teller machine, which is the ATM machine, and printed circuit board assembly operation, runway activity at airport, traffic flow, financial markets, telecommunication systems. In all these examples or in all these fields, we apply the stochastic process. And there is another definition called state, snapshot of the system at some fixed point in time. So, at a particular time, for example t, so the state of the system, which is given as snapshot. So, snapshot means within a particular second. So, a snapshot of the system at some fixed point in time, that is called state. So, what is the state of the system at some particular time? Similarly, transition, movement from one state to another state. So, first there may be many states with respect to a particular time t. And if the system, if we are moving from one state to another state, that is called transition, the change. So, a stochastic process is a family of time indexed random variable xt. We denote it by xt, or else we can use the notation x of t. That means this random variable depends on the time t. So, it is a family of time indexed random variable where t belongs to an index set I. So T belongs to this index set I, which is a subset of a set of real numbers. And to give an example of that index set, we can consider from minus infinity to plus infinity. So this interval is denoted by capital I, which is the index set. Similarly, the lower limit is 0, upper limit is infinity, or else some finite values also we can take 0 plus or minus 1 plus or minus 2, 0, 1, 2, 3 and so on. Here the first two are continuous because the infinity is involved, and here in the remaining two are discrete time stochastic processes. And here we use the uppercase letter. So this capital X suffix T, where the T denotes the time on which the random variable depends. So xt to describe the process, uppercase letter xt to describe the process. A time series xt is a realization or sample function from a certain process. So if we consider a particular process, then this xt gives the sample function using which we can study the entire process. And also we use information from a time series to estimate parameters and properties of process xt. So we use information from a time series. So how the random variable changes depending on different time values. So we can define a stochastic process as it is a set of random variables. If you want, you can denote it by x suffix t or else x of t, depending on some real parameter t, where t is the time. And this process is also called random process or random function. So a stochastic process is a set of random variables capital X of t, which depends on some parameter t, which is the time. And as an example, a queuing system is a random process or stochastic process. You know, in queuing theory, we study a queue and different properties of a queue. And here the number of persons joining in a queue and the number of persons already served in a queue, these are the random variables. So this queuing system is a random process or stochastic process, since these two random variables depends on time t. These two random variables depend on time t. Similarly, experiment of throwing an unbiased die. Let us consider an unbiased die. So a single die is thrown. A die is thrown. Then the outcomes are 1, 2, 3, 4, 5 and 6. Now if I denote xn as the outcome in nth throw. So a single die is thrown, for example, n times. Then xn denotes the outcome in the nth throw. Then the set xn such that n greater than or equal to 1. Obviously, we need to conduct the experiment at least one time. So n greater than or equal to 1. This set constitutes a process which is called Bernoulli process, and this is an example of stochastic process. And coming to applications, just now we have discussed in the initial slides that telecommunication system is one of the examples of or one of the applications of stochastic process. So the number of telephone calls received at a switchboard during the time 0, t. In that case, xn, t belongs to capital T, where t can be any time from 0 to infinity. We can consider any time in between these two values. So this constitutes a stochastic process. So in telecommunication systems, we use this stochastic process. Similarly, in fluid mechanics also, turbulent fluid flow. In fluid flows, the velocity components u, v and w, these are the random variables here, random variables which depends on the space variables x, y and z. So in fluid theory also, the particles moving in the moving through the fluid, that depends on the time and hence it comes under an application of stochastic process. And movement of molecules in a gas or a liquid. In gases or liquids, we know that the molecules move with certain velocity and they collide with each other. So, they collide with other molecules. So, molecules collide with other molecules, and here velocity and position are the variables, and again it depends on time. So, the entire process comes under stochastic process. So, we use the concept of stochastic process in all these cases. So, in molecules, movement of molecules, in fluid flow, and in telephone calls, we apply the concept of stochastic process. Similarly, there are some other examples. A random walk model. For example, a particle is moving in a straight line in steps of unit length. So, a particle is moving, for example, here it is moving like this. At every stage, it can move one step left or one step right. Suddenly, it may go like this, or else it may go right side also. So, it may go left side with probability small p, and it may go right side with probability q, where q is 1 minus p, since p plus q equal to 1. So, at every stage, it can move one step left with the probability p and right with the probability q, where p plus q equal to 1. And here, all these movements comes under random process. It constitutes a random process. Similarly, in communication process, the amplitude of signals to be transmitted and the amplitude of the noise produced, the amplitude of signals to be transmitted and the noise produced in the channel depending on time t, and here both are the random variables, and the entire process is a stochastic process. And there is another important one. Even in gambling also, we apply this stochastic process. So, this particular example is called gambler's ruin problem or classical ruin problem. For example, a gambler is playing a game. A gambler wins or loses one unit with probabilities p and q respectively. For example, if he wins, the probability of winning the game is p and losing the game is q. Now, let x be the amount he has. The player has the amount x and his opponent has a minus x. That means, what is the total amount is a. Let x be the amount that the player has and a minus x is the amount of his opponent, and the total credit is a. Now, the gambler plays the game until he get the total amount a. That means, whatever the opponent has, he want to grab that amount. So, he continues the game until he get the amount a, or else until he remain with 0. That means complete losing. So, here the total capital is a random variable, and the probability distribution of duration of game is a random process. So, hence this is the best example of a stochastic process. So, in gambling also we apply the concept of stochastic process. And coming to specification of stochastic process. So, particularly here just now we discussed about a state at a particular time t. So, at a particular time t, the set of all possible values of an individual random variable if x is a random variable, let us consider all the possible values of that random variable and form a set. The set of all possible values of individual random variable of a stochastic process. So, what are those values? In general, we denote a stochastic, in stochastic process, the random variable is x of t, xt or x of t. So, all the values of xn where n greater than or equal to 1 is known as a state space denoted by I. So, the set of all possible values of individual random variable in a stochastic process. So, this state space is either discrete or continuous depending on the number of points. It is discrete if it contains a finite or countably infinity of points. So, if the number of points are countable or it contains finite number of values, then the state space is called discrete state space. Otherwise, it is called continuous state space. Otherwise means if the discrete random variable takes infinitely many values. And as an example, let us consider a fair die is thrown. Let xn be the total number of sixes appear in the first n throws of the die. Let xn be the total number of sixes appear in the first n throws of the die. Then the set of possible values of this xn, if you find all the values and write in a set, that is called state space. So, here it is a finite set of non-negative integers. Since a die is thrown, the outcomes can be either from 1 or 2 or 3 up to 6. And here number of sixes. So, 0 sixes, 1 6, 2 sixes and so on n sixes. For example, n times the experiment is repeated, but all n times we got 0 sixes. There is no 6. Or else, if n times the experiment is conducted, one time we got 6 or 2 times, all n times. Like that, these are the possibilities of that particular experiment. So, the random variable takes the values 0, 1, 2 and so on. So, this is the state, this is called the state space, and here in this particular example, this is discrete since the set is finite. Hence, xn is discrete. So, this is about the introductory part of stochastic process. Simply, a stochastic process means a process that depends on time t, a random variable that changes with respect to time. In stochastic process, we have discussed some examples and applications and some important definitions also. In the next session, we will discuss about different types of processes and steady and transient state processes and transient matrix and some examples that we are going to discuss in the next session. Thank you.